Again, it's me, Billy Younger, with Physics Solutions. This time I'm asking the question, given a sample of copper, 73.0 grams, how many atoms are actually in that sample? So again, I ask you to pay attention to each number you use in the calculation, just like we did in the previous one where I took and converted the 73.0 grams of copper to the number of moles, which by the way turned out to be about 1.1, somewhere around there. So let's try this again. I'm going to start by sharing my screen with my iPad. Hopefully that don't take as long as it sometimes does. So it should come up any second. So again, you see you are given a 73.0 gram sample of pure copper, the atomic weight of which is 63.546. How many atoms of copper is in that? Note, pay attention to each number you use in the calculation. So in this case, what I'm going to do is I'm going to interpret this molecular weight not as grams per mole, but as atomic mass units per atom. So we can now say MCU, it's molecular weight of copper, is equal to 63.546. And we already used in the previous problem the fact that that unit is grams per mole. But this time we're also going to make use of the fact that it's also 63.546 atomic mass units per atom. So what I'm going to do is I'm going to take my sample, which is 73.0 grams, and this time I am going to actually divide it by the number of atomic mass units per atom, and then of course I've got to convert that number of grams to kilograms, because basically we have a conversion for U that goes to kilograms or grams. So if I take the 73.0 grams and I divide it by 63.546 atomic mass units per atom, and actually I should probably center this up a little better, so I'm going to do it this way. This is all the denominators, so now I'll put the fraction bar a little bigger and put this right here. Now, I can't just blindly divide 73.0 grams of copper by 63.546 atomic mass units of atoms. I mean, I can, and that gives me a number. It just doesn't give me the right units, and it's essentially meaningless until I convert this mass unit, the atomic mass unit, to grams. So to convert the atomic mass unit to grams, what I'm going to do is realize that 1.6605 times 10 to the negative 24th grams is equal to 1 atomic mass unit. So if I do that, I'm going to take 73.0, and I'm going to divide that by, here I use parentheses just in case you're rusty on your arithmetic and algebra. You are supposed to use parentheses if you just put this in your calculator, or else you'll end up dividing by 63.546, but multiplying by the other number, and that's not good. So I'm actually now dividing by parenthesis 63.546 times 1.6605 e to the negative 24th. And then I'll close my parenthesis, and the answer is 6.918 times 10 to the 23rd atoms. So it seems that this the 73.0 gram sample of copper, which we already know from the previous calculation is slightly larger than a mole, has slightly more than Avogadro's number of atoms. In fact, we can now use this to specify exactly what's happening. And actually, to specify another way of doing it, I could do this. I can take 73. So let me write this down. I'll say alternative solution. So this alternative solution, I'm going to take the 73.0 grams, and I'm first going to convert it to moles by dividing 63.546 grams per mole. And then since a mole is made up of Avogadro's number of atoms, all I have to do is multiply that by Avogadro's number, which for me, it'd be close enough to say 6.022 times 10 to the 23rd reciprocal moles. That's the units of Avogadro's number. So if I just take 73.0 and I divide it by 63.546, of course I get the 1.149 moles that I expected. Now I'm going to multiply that by 6.022 e to the 23rd reciprocal moles. So that says, in fact, that we get 6.918, again carrying one extra sig fig like I did before. I should have underlined it before, so I just did that now. But 6.918 times 10 to the 23rd atoms. Atoms. Okay, because in this case, we could actually put, instead of Avogadro's number being just reciprocal moles, we could actually write it as atoms, since it was an atomic weight instead of a molecular weight, in which case I would have said molecules per mole. So in looking at this, you see that basically what we did is we divided the mass of the sample by the atomic weight, and then multiplied messed up again, got my letters out of order. Multiplied that answer by Avogadro's number, which I won't try to spell Avogadro because I'm probably going to make a mistake. I'm just going to say Na. So that was in the alternate solution. So I'll write okay, but in the original solution, let's say original solution, we divided the mass. I'll call it M this time. I probably should have done it the last time too, but I didn't, so I'll just do it there. We divided the mass M of the sample by the atomic weight using the units of atomic mass unit per atom. Then we divided that answer, that number of moles, by the conversion factor between grams and atomic mass unit. So if you just look back at this, you can realize the only way this is both giving us the same answer, which it clearly did, is if in fact the conversion factor we used for grams to atomic mass unit is in fact the reciprocal of Avogadro's number. So the fact that these two are equal implies that these two are equal. And of course, that means the conversion factor is 1 over Avogadro's number. So here's yet another way we can see that it's perfectly reasonable to make the assumption that the conversion factor between grams and moles, between grams and atomic mass units is 1 over Avogadro's number. And if you actually wanted it in kilograms, if you want to convert atomic mass units to kilograms, then it'd be 1 over parenthesis 1,000 times Avogadro's number to make that 10 to the negative 27th as opposed to 10 to the negative 24th, which is the difference, of course, between grams and kilograms. So I hope that helps. And that's it.